Hi everyone and welcome. In this talk I will walk you through our recent paper, Learning to Rank Features to Enhance Graph Neural Networks for Graph Classification, published in Transactions on Machine Learning Research. Over the last few years, we have seen a clear rise in research focused on feature learning in graph neural networks. This growing trend is not surprising because the distinguishing power of standard vanilla GNN is fundamentally bounded by the first dimensional Weisfall element test, 1WL. Let's look at a concrete illustration of this limitation. Consider these two graphs, G1 and G2, belonging to different classes. A vanilla GNN fails to distinguish between these two graphs because G1 and G2 appear identical under 1WL, as nodes have the same degrees, 2. So the model assigns them identical representations, leading to misclassification. However, if we enrich these graphs with a simple feature like node eccentricity, which is the maximum distance from a node to all other nodes, now the GNN separates the two classes correctly. And this leads us to the key question. Which features should we add, and how do we select them for each graph classification task? So choosing the right features is very important, and there are two main lines of prior work. First, there are approaches based on predefined static feature set. These sets are fixed in advance and contain set of features like node degree, page rank, centralities, clustering coefficient. But these methods require domain expertise, and the same feature set may not work across different tasks. Second, there are dynamic approaches. They offer more flexibility, but they are limited to local graph patterns. So we still have this problem. We don't have an automatic way to pick most relevant features for each classification task. And our approach addresses exactly this challenge. So the method defines a large set of candidate features, and for each task, we automatically select the most relevant features. A crucial property in this method that these features are selected without computing them first. How we do this? We are to predict relevant features with a feature ranking GNN. So the method starts by dividing the dataset into two parts, one for feature ranking and the other for graph classification. The first step is training a feature ranking GNN. So for each graph in the feature ranking set, we first compute the full feature set of candidate features. Let's say C features in total. And using this full feature matrix, we train a random forest classifier to predict graph labels. From the random forest, we extract feature importance scores, and this gives us a feature importance vector for each graph. We then train a feature ranking GNN or FRGNN that learns to map each graph to its corresponding feature importance vector. Then in the second phase, we switch to the actual graph classification task. And for each graph in the graph classification set, the learned FRGNN model predicts a ranking of all features. We then compute only the top K features, not all C features, and these top K features become the input to the final graph classifier GC-GNN. So with this setup, we ask two main research questions. The first one, does using only the top K features improve predictive performance compared to using all features? And the second one, are the selected top K features really informative, or they could be just accidental? And to answer these questions, we conducted extensive experiments on both real-world and synthetic datasets. We start with 13 widely used datasets from molecular chemistry, bioinformatics, and computer vision. These datasets cover different scales, some containing up to 40,000 graphs, and each with up to, in average, 500 nodes and 600 edges, and with different classification tasks, from a binary task to a multi-class classification with 11 classes. Going to the results, so compared to using no features at all, F0, our method delivers a 14% improvement in accuracy. And when we compare our top K feature set, here top 6 features, to using all the features FC, we still see a 7% gain. And the feature selection truly matters, because our top 6 features outperforms a random 6 features sampled from the whole feature set with around 10%. And overall, our approach either outperforms or closely matches state-of-the-art results across different benchmarks. Then, to evaluate our method's ability to detect structural features defining target classes, we conducted experiments on synthetic graphs with known ground truth. So we defined 6 learning problems, and for each of these problems we generated 4 data sets, each with 600 connected base graphs from one of the 4 standard random graph models: Erdos-Renyi, Barabashi-Albert, Watts-Strogatz, and Power Law cluster. So we defined the target classes using 4 distinct graphlette motifs: the house graph, the hexagon, the 4-click, and the path of 5 vertices with 2 chords. None of these graphlets is subgraph isomorphic to another. So we defined 6 problems, and each with 4 data sets. So we have in total 24 problems here. Going to the results, we see that our selected top K features deliver substantial improvement. They outperform the no feature baseline F0 by at least 50%, and they also achieve performance comparable to using the full feature set FC, while clearly outperforming a random selection of 6 features R6. And this confirms that the features selected by our method are both meaningful and highly effective. Then we analyzed the runtime. So our total pipeline includes computing features for the FRGNN, computing the top K features, training the random forest, and training both GNN models, the FRGNN and the GCGNN. So as we see here, for large-scale data sets, our method achieves significantly lower runtimes, sometimes by more than an order of magnitude, while preserving or enhancing the predictive performance. While on smaller benchmarks, as we see here to the left, the feature ranking phase adds a minor computational overhead. However, this cost is negligible compared to the consistent improvements in the classification accuracy achieved by the method. To wrap up, our method automatically identifies a small set of truly important features for each graph classification task, and crucially, we only compute these selected features for the target graph, and despite using only a handful of features, these selected features can boost the accuracy of the graph classification model. If you would like to explore the details, check out the paper, and thanks for watching.